Another DraftScience video presentation. Uh, Human race. All right, so I'm going to challenge, one of these basic premises of physics. Something I would have felt comfortable saying just a few months ago, probably. Saw no real reason to deny this function, this energy conservation idea that you can never create or destroy. Well, you can't create, but you certainly can destroy, I would argue, in some sense. From the total universe's perspective, the amount of movement there is can't make too much difference. The fact is if they arrange matter here and then run a universe, it can't really, the energy equation isn't going to appear to be any different. But the truth is, if I have to move stuff here and then I move it back here again, I did do something, and I did something that probably is wearing the universe down. So there could be an argument anyway that can be made where the trail of the energy gets lost. Where you can't follow it anymore if it still exists as easily. So anyway, I'll play the statement and I'll play around with the subject of gravity a bit more.
And the molecules in the flame that are moving very rapidly transfer their kinetic energy first to the bulb and then to the gas. Now, some of the energy of the flame goes into the energy of the gas.
Sorry. I thought I started at the right place, but I didn't.
And the temperature goes up and the pressure goes up. Now, what do we mean by the principle of conservation of energy?
So anyway, just the words, the pressure goes up, just brings up the idea of what atoms are doing. And in a way, atoms are, or let's just say all of them are created inside of high pressure. So let's go with the idea that elements aren't something you can just create on your desktop kind of thing. They require a special environment for you to take elemental pieces and somehow form an atom out of the elemental pieces. A lot of pressure. So it only happens in these extreme circumstances where there's a bunch of free energy, in the sense of a bunch of this stuff I'm calling force. And they have to be pushed together and forced into a relationship where they're in a really high pressure environment. And then the fact is that 100 of these elements, a little bit less than that actually, are stable enough to stay intact even when you take them out of the high pressure. So it's like having some kind of sea creature that lives, in the bottom of the ocean under very high pressure, and you bring it to the surface, and most of them will just explode and turn into mush, goo. But I guess there might be some of them that can take the pressure differences, that survive it, at least for a period of time. And that's sort of what atoms are demonstrating, is that they can survive. They're such a tight, perfect, efficient little machine in terms of how the force is moving through them, that they can survive taken out of pressure. And then the trick is that some of these elements we can, like lithium or iron, we can change them in such a way where they can absorb a little extra energy or they can release a little extra energy. We can fill them with some more or take some out, and they still survive that process, to an extent. Obviously, you can blow up some lithium batteries, but anyway. So, continuing.
Energy appears in various forms. There's kinetic energy and potential energy.
So let's understand, potential energy is kind of just a fake word in a sense. It just has to do with the fact that you've moved energy from one place to another. Now, if you're going to say it's potential energy because I hold the battery up in gravity, well, it has nothing to do with the battery. The battery doesn't have any more energy. You didn't do anything to the battery. The battery doesn't really care. And what you really have to understand is there's a real force, a real active force in the universe is that it's going to be moving the battery. The battery's not going to move because the battery wants to move. It's not inside the battery, the motion. The battery isn't trying to go somewhere. All right, it's the atmosphere it's in, the universe it's in. If I draw a circle around the battery and look at what's in the universe the battery's sitting in a universe that's saying you're going to go down. There's more energy, in fact, above it than below it, and it's going to move because of that differential in the real energy that it's surrounded by. Now, it hardly has anything to do with the potential of the battery. So this whole, it's kind of a gooey, mushy concept, and the whole kinetic thing is, again, broken. This 1/2 mv squared notion of a formula is just a nonsense. It should have never been adopted by physics. There was no good reason to think the energy of an object is anything other than its momentum, its movement. Movement is the signature of energy. That's how you see where energy is because it's moving something. If something's moving, it's in an atmosphere where energy is revealing itself by showing that there must be stuff hitting it, because more stuff is, it's moving one way than it is not moving another way, and it's just the obvious indication. Where something's standing still, okay, it doesn't look like it's in energy, but everything's in energy. The whole universe is full of it.
And, sometimes it's orderly, and sometimes it's random.
Yeah, so the point would be is that inside an atom, it's orderly. Okay, you're pushing force in, and it has to stay orderly. It has to find a way to do the circular thing. It has to be in such an arrangement where it can't escape. And obviously, the easiest way to make it not escape is to fool it into just going around and around and around. And so you can trap motion. That's the simple argument. Okay, motion is just a thing, and you can have motion, okay, back and forth. You can have motion in a circle. You can have different kinds of motion that are orderly, okay, can stay that way for a long time, and you can have motion that doesn't stay the same. And so that would be the only words you would use is, in terms of the order just has to do with staying in the container, more than anything else. Confinement is the only kind of order, really.
And when it's random enough, we call it thermal energy. Some people call it heat.
Yeah, well, it's all heat. So everything's heat. Everything moving, all the force bits moving the speed of light are going to, in one way or another, they're just plainly describable as heat. It's motion, and it'll cause other things to move, which will be motion.
What we mean by the principle of conservation of energy, then, is simply this. We believe that energy is never created, never destroyed.
All right, so my argument would be is its destruction in the universe is why we have gravity. So the fact is, well, I'll play the rest of this. There's no point in coming back to it, I don't think.
We may convert it from one form to another, from orderly motion to random motion.
Yeah, but the point is you can use it and create no construction that can be seen by the universe. So again, this motion, all right, can't really be anything. It can just waste energy. You can just consume it. There's less energy in the universe if the universe is busy doing this, where it's not really gaining any distance. It's not really creating any capacity to dramatically change the universe, just because the universe can't anticipate the fact that it's doing something aberrant. It's not even the way to do it. It can't catch up. The rebound speed is slower than the injection speed, and in a sense that consumes the energy. So the basic principle is, so if we have gone over, and I'll attempt to extend it to a more other subjects. Just so the idea is that for an atom to move, the elements inside the atom have to move, the electrons and the protons, and they can't move on their own. They can only move because a bit of force hits them and pushes them. So if they go to a new location, they do it being pushed by an actual element of what is called force, momentum. And when the force is acting, it goes from going the speed of light to going slower than the speed of light, because the electron won't go the speed of light being pushed by one little piece of element of the force. It has to be pushed by a whole bunch to get up more speed. So this can only get to maybe 10% of the speed of light. So it's lost by pushing matter. It's lost momentum. Its practical fact is it won't travel the same distance in the same amount of time, and it can't be said to be going the same speed. It only travels this far in the same amount of time. So it's clearly lost something called energy. Now the trick is the matter is moving, so in that sense it's still moving, but it's moving much slower, and it's only moving as big as this atom can absorb energy. So depending on the size of the atom, the size of the electron and how much space it's exposed to, that's the only way the universe can account for the energy loss, is to say, what did this thing do by moving from here, from point A to point B? What did it change in that process? And I would argue that it's not going to be able to change enough to compensate for what it lost here. And so the implications would be the universe does slowly wind down, just because there is no new source that we know of this energy stuff. Now there could be. The universe could be pushing out, some minor new amount of energy into the universe through some process, but we don't know what that process would be. And there could be something more complicated in the fact that when this electron does move, that it has fully accounted for this lost momentum by creating more momentum in some other place. Now, it can't make a force move faster, but it can make a force reflect sooner. And by reflecting forces sooner than they would have reflected, you might be adding energy to those bits, in the sense that the distance they travel won't be reduced, but in a sense it will be. They went more distance because they didn't have to go as far to hit something. So this distance and a reflection is going to be longer than this distance and the reflection. And so in a sense, this one has. This one's going to get to this point B sooner than this one's going to get to point B. If it's, let's just say I should call it point C, right? Okay. This is point A, point B, point C. Okay. So this one's going to get there sooner. So in a sense, that means it has logically more energy. Okay, because if you were to convert that into speed or momentum, you'd have to argue it has more momentum because it traveled, what theoretically, if this was the same difference, if you average this, the argument would be is this one did it in less time, but the point B is what you changed. Just saying, so from the universe's perspective, that's an increase in its energy, and that might be compensating. So anyway, that's one underlying argument that could be made. Shouldn't do this, but I'm doing it. Gotta get better organized. Anyway, seems to be a little bit of a lag, but well, whatever. Sync issue. Alright, so what I wanted to get to is gravity. So the point is that gravity is the consequence of little stuff moving inside of big stuff. So when the little stuff inside of it is moving in all kinds of directions, it's doing exactly that thing there. It's pushing, the force bits have to push the atoms. That means that they don't go as far as they should, and so you have a disequilibrium, in the sense that more little bits of energy are going in, okay, than are coming back out. So what comes back out is less than what went in, and that's gravity. And each thing creates gravity. So if I have two things interacting with each other, it's really not some kind of thing where you want to think about it in terms of combining both masses. So the cliche formula says G times M1, M2, R squared, combining the two masses. Well, it really isn't. I mean, that's how the whole game will be played, in the sense that this one's going to pull on that one and that one's going to pull on this one. But the truth is they're not going to do it based on their masses or their weights, aren't going to change the fact. This one's going to have a certain gravity that's going to affect this object, and this object is going to affect this object. They're not going to blend the forces, okay? It's just an explicit fact that this one is not producing as much radiation. So the radiation coming from here is less than the radiation that exists out here. And that's a fact for this object. And the same fact exists for this object, that this one is going to block some radiation by moving stuff this way. It's moving stuff that way too, so it's creating gravity in both directions. But anyway, and it's going to affect this object because this one's going to have less stuff heading for it. So gravity is pretty much, you don't need the MM thing, okay, to tell you what this thing's gravity is, or this thing's. They're all insulated and unique to each object. Each object creates gravity. There's no I'm doing it collectively stuff until you put a third object in, and then you can say, well, how much is this one plus this one add up to how it affects this third one. But they're, it's just I don't think, a very constructive or productive way to think about it, in terms of always thinking about the two objects, because each object is creating the gravity uniquely. It doesn't need to convey it. It doesn't need to, they don't sit there and report to each other and all this other stuff that people, even I, in thinking about it 5 years ago, I might not have seen that how clear that distinction is, that this gravity has nothing to do with this object at all, and this object doesn't have anything to do with this object, and it's just the way it is. Beyond the fact that obviously if I'm standing here, okay, that there's the outside force hitting me all around. If I was standing over here, it would be completely different, right? I mean, if I'm standing on this side, okay, then I'm getting this blocking plus this blocking is affecting me. Where if I'm standing here, it's exactly the opposite, in the sense that this force is a little weaker because the object's in the way. So I'm not getting hit by the universe here. I'm getting hit by the universe minus the effect of this. And so this gravity is going to be weaker in terms of the gravity I'm going to feel from the Earth, because this object's in the way, okay, tending to, say, go that way a little bit. Now, it's clearly not strong enough to overcome the gravity here, but I'm just saying that it's an obvious fact that once you put another object in there, you're not measuring against the outside of the interaction between the two objects, and that's the full pressure. So I mean, obviously you can be in places where the pressure is more complex than just one thing's effect, but it doesn't change the fact that this gravity, the lack of energy coming out of the moon, let's call that the moon, the lack of energy coming out of the moon in all directions doesn't have anything to do, in a sense, with the lack of energy coming out of the Earth or the sun or anything else. So gravity really isn't some kind of interaction between two things. It's an interaction between what this is doing to the, looking at it, what it's doing to your environment by being there, being out there. Okay, it's absorbing something. So even though the sun's producing light, it's really absorbing energy from the universe, because the sun has a bunch of pieces moving, and the only way the pieces can move is to be absorbing energy from the universe, to have taken it and consumed it to move the little bits around. The little bits can't move. They can't stop at the surface of the sun. They can't do any of the things they're going to do to stay in the sun unless you have the pressure of gravity. That is, this deficit that they're creating by moving. So obviously every time something tries to move out, the only way they can move out is to absorb energy going this way, and they have to essentially absorb it because it came in that way. And that's what they're absorbing, is energy that came into the sun. So even though the sun looks like it's self-contained, the only energy it's actually producing is the the photons. And the gravity is happening for, irrespective of whatever thermal temperature the sun is at, because it's burning atoms or combining atoms. That energy doesn't have anything to do with the fact that the sun's total energy is a byproduct of also the universe sending energy in and also causing movement. I mean, it's still a movement in. It's still an aggressive bit of heating. Okay, so the universe is sending energy in and heating the sun, moving the bits, and that energy is still slowed down, and that's why the sun still has gravity, even though it appears that it's producing more energy than the universe is pumping in. I mean, you don't see any of the energy that goes in. You're just seeing the energy that comes out. So you have a very distorted view of what the sun is doing. But again, if you measure the gravity, well, then you can see the energy that's going in. But then let's understand, the energy is not that dramatic. On the surface of the sun, the gravity is only 8 times what it is on Earth. Is it 80 times? 80 times? Let me just think for a second. 80 times? I think it's 80 times. Well, anyway, it's not as dramatic as you would imagine for something that's 1,000,000 times bigger, just because it has so many, the atoms they're so much further away from each other. So the Earth has, the average atom on the Earth is, looks like this, and the average atom on the sun is, doing this. I mean, they're much more spaced. So the sun's a lot less dense. But they're obviously moving quite energetically. What it has is moving very fast. So, but the fast movement again is just evidence that something's pushing all those little bits around, and a big part of that something is the universe sending a bunch of stuff in, and it's not getting out in the same time. And that's just a constant feature that's happening all the time. It's all the time. It's taking more energy in than it gives out, more energy in than it gives out, and there's a constant differential, and it's just a constant amount of lag in how the force goes in and gets out. So as long as that lag exists, it means a certain percentage of the total force that was in the universe, 10% or whatever, is stuck doing this. And this takes time, which means that there's more energy in here than it's getting out here, because it's taking time all the time. Every second, it's taking, every bit of new energy that goes into the sun is doing the same thing. It's going through the obstacle course. And that obstacle course is dictating how big a differential there is between the energy coming out of the sun and the energy going into the sun. Yeah. Alright. Let's see, don't want to do anything else. I don't know. Yeah, I don't think so. It's just, we'll play the end of this, I guess, right? Well, it's not much left, so let's see how they conclude. It was just the basic stuff, just the idea that the energy moves from object to object, so you can just kind of understand that the energy is really hitting electrons. The electrons are moving the other electrons, and the electrons and the protons are also tied together by little pieces of energy. So everything ends up being moved, and then, so all you're doing is taking energy and the form of one soldier, and then you're putting the soldiers on trucks and then moving the soldiers on the truck, or whatever metaphors you use. But the little bits of momentum do travel through the systems, making big things move, little things moving, blah blah blah. But it's all motion in the end, and that's all there is motion.
We may fritter it away by warming up the air, by warming up the ocean, but it's still somewhere.
So the argument would be is that you can imagine that there could be a circumstance. Let's say I could make the universe. I was just making my own universe, and in a sense, you could say, okay, how hot is the universe, or where's the energy? But what if I did have a trap, an atom? And so I have a certain amount of energy in the universe. Let's just say we have 3 pieces of energy in the universe, and one piece can just bounce off the walls, whatever the walls will be, and it just flies around. But one piece goes right into a piece of matter, and it gets caught, between electrons, and it does this. It's just stuck, taking right turns, takes a right turn, takes a right turn, or even just going back and forth. Getting stuck in a bucket. Here's a bucket, and it hits this wall over here, and it gets stuck inside the bucket. It's just going back and forth. It could be doing that forever, right? So if energy goes in and it gets stuck in a trap, you can sort of understand that, well, frankly, the universe is going to look awful cold, because if that happens to this piece, and then it happens to this piece of energy, and then it happens to this piece, then all of a sudden there's no energy in the universe, because it's stuck inside of matter doing this. So matter, E equals mc squared is, a reasonable approximation. Okay, I don't think it's exactly c squared, but whatever. It's a reasonable approximation, because that's exactly what's happening, is that matter stores energy, in the fact that it gets stuck as pressure inside the atom, keeping the electrons and the protons in balance with each other. So these could just be understood as electrons, and they're just diverting energy, storing it. And the same thing is happening in the nucleus, as little energy is being stored in motion of the little bits, the protons. And so there's a bunch of energy in there, because the energy is what's keeping these things in their positions, what's keeping them from that's what's keeping the atom from falling apart, is the pressure that's built into the atom. But it's hard to say that. I mean, in a sense, that's a destruction of the energy, because it's not going anywhere. It's not getting anything done. It's not doing anything. Okay, and now it has arranged these objects in a pattern, but if the pattern doesn't change and nothing changes, then the universe looks pretty much dead. So in a sense, the matter is cooling, consolidating the universe. And you could argue that if all the energy goes into the matter and gets stuck, well, then you can imagine there's less energy here on the outside, right? Now you have less pressure pushing in to keep things together. Now the motion that this thing wants to move out, well, all of a sudden now all of that pressure can't be stopped, because there's nothing on the outside to push in. So you can see that if the more of these atoms I create, the less and less free energy there is, and the less free energy there is, that means the less gravity there is, and that means the less holding all the little pieces together. So you can, I can understand. I'm not saying this one's the truth. We're a long way from knowing with a certainty, but the fact is galaxies in the past are very compact compared to galaxies now, right? So galaxies now are big, okay, and less bright, and they were brighter and tighter, okay, 13 billion years ago, all right? That's why we even call them something different, quasars, So we didn't even know they were galaxies. They were so different, okay, than the newer ones, the ones now. Well, you could argue that the difference is that the universe is in a stage. The stage is the gravity started decreasing because the matter got more and more compact. And as the matter got more and more compact, it was pulling energy out of the outside and putting it on the inside, right? And the vice versa is happening. So now the galaxies, because there's less gravity, G actually changed, the constant, because now we have less energy in the field. The galaxies are expanding, which is pushing energy out into the field. So now the field is gaining potential energy, and vice versa. That'll mean it'll crush the galaxies again, and then it'll expand them again, then it'll crush them again, and then it'll expand them again. And you don't need a big bang and all that kind of stuff, obviously. So it, does create an interesting side subject.
Now, there's one more thing we've got to discuss before we finish.
Cool.
Now, when we transport
we have to go to the window to do it. Kind of funny.
Energy, we might transport the whole material body, complete with the energy and all, like throwing hot rivets or carrying coal.
Or a battery. I can just pass it on.
Or we might have energy transported by molecular bombardment. We've just been discussing that. We call it heat conduction. Or energy might be transported.
So the heat thing is interesting, just because that's really requiring there to be a transfer between atoms moving. But again, the atoms don't move unless the little bits inside the atoms move, and it's the little bits that have to transfer all the energy. So the atom doesn't move until it's moved by the little bits. So in a sense, it's just measuring the gravity or the charge or the movement of the little bits that are really moving the atoms around. The atoms don't move by any magical force. An atom only goes from point A to point B because a force forced it to. There has to be a force. There's no magical repulsion and no magical attraction. It's always got to be created by an imbalance in force.
By radiation. Usually this takes the form of electromagnetic radiation, say infrared light, or visible light.
Or any of it, right? So we know all of it will heat something. All the radiation heats something. All of it. We call it infrared, well, and imply that that's heat. No, that's just weak microwave. I mean, you could argue it's strong microwaves, right? Yeah. But that's it. It doesn't have anything to do with it being something other than what all the rest of the stuff is, which is vibrational potential. I mean, in the sense it's bits traveling at a frequency, and each frequency has, it's like you have a bunch of bullets, not just silver bullets, but gold bullets, platinum bullets, titanium bullets. All the bullets kill different little monsters. So each atom is vulnerable to a different color or a different kind of bullet. So depending on the bullet, depends on what happens to the object. I mean, like some stuff, like whatever, it's a gallium or whatever the hell it's called, it melts in your hand, so a little bit of heat, and it's already changing its properties.
In fact, most of our energy comes to us that way. It comes to us from a star, our own personal star called the sun.
So the irony is, the sun is producing more radiation at a certain frequency, visible light range, there's a lot of it, so most like 90% is visible type style light that comes out of the sun, and then there's the other percentages are the radio waves and the there's still a lot of radio waves, so it's 90% is an exaggeration. Let's just say 50 for the sake of argument. Well, let's say 70% is visible. Visible is the peak, and then you have the weaker radiation on one side, and then the gamma rays and the X-rays on the other side, and they're it's a very narrow band of those. Broad band of these, but not, by comparison to the volume of visible light. Visible light's the bigger block, and these other radiations, radio and whatnot, are a smaller block, and then this would be an even smaller block for X-rays and gamma rays. But anyway, but the truth is it absorbed a whole bunch of momentum from the universe. The universe is shining more light in those invisible ranges that you don't see. Much more of it's going in than is actually coming out.
In the sun, the energy is stored by the atomic nuclei. And this energy is converted into random thermal energy in the sun, and that random thermal energy into radiation.
So there's nothing really random, obviously, but so the conversion is there's pressure from the outside world. There's little bits of momentum going in at all kinds of, no frequency, but you wouldn't call it random because the universe isn't random. But yes, it's for the sake of argument, it is close enough to random, and then it comes out in these more ordered forms of visible photons that are actually just the atoms. Okay, the atoms are getting bombarded by all this pressure, and the atom basically changes shape a little bit. Electron flies out here, and then it goes back over to here, and then goes back over to here. It doesn't. It's not. They're not jiggling perfectly, and the jiggle of the electrons inside of the atom means the atom changes its shape, and as the atom changes its shape, it means it reflects at a different point, and so it pushes into the stream of energy that's coming in, and it compresses it into clumps of energy at certain locations, depending on when it pushed out and when it pushed in, when it pushed out, when it pushed in. So as it pushes out, it condenses the field and creates, what we see as photons, which are just that idea of an electron moving, and that is causing periodicity, okay, in how the energy is released back out, how it's escaping. So the energy goes in, it bounces around inside the sun, and then a lot of it comes back out because of how electrons are moving inside of the atoms that are hot inside of the sun, and they're pushing the energy back out by pushing on the energy going in, reflecting the energy coming in.
And the radiation comes through space, and some of it is captured here on the Earth. And some of that, by the process of photosynthesis, is converted into trees.
Yeah, well, this gives me an excuse to do the, for all the climate change deniers. I mean, this is just the simplest argument, demonstrating, the process, right? Because we know the trees, they're not like modern trees. Like 300 million years ago, there were all these different periods. There was mass extinctions, this, and this, but there was a ton, and there were periods when the Earth had a ton of vegetation. It's like stuff grew everywhere on everything, and all of those trees die inefficiently in the sense that they aren't turned into compost. Okay, they aren't put back into the biosphere. They die and lay on top of each other and lay on top of each other, and their corpses get buried. And as their corpses get buried, they're sinking carbon. That is, they took carbon out of the atmosphere, they put it into the wood of the tree falls down, they fall on top of each other, they sink into the earth, they're buried by glaciers and other kinds of crap, and they sit in the earth and and store a ton of carbon. The carbon doesn't get back out into the atmosphere because it's under the ground. And it's happened with methane and coal and oil and gas, and all these things are just storage of a ton of carbon.
And the trees will...
And the fact is the world did change. It went from being hot, okay, because you had more oxygen in the atmosphere, and you had more carbon dioxide, and that meant you could hold more water in the atmosphere. Okay, so that combination, water is the real greenhouse gas. That's the strongest of greenhouse gases, essentially water vapor. And so the more water vapor you can hold, that is, the hotter you can make the ground, the more moisture is going to end up back in the air. And so carbon, just in a sense, is a catalyst to creating capacity to hold more moisture in the atmosphere. And so it was much warmer. That's why there were dinosaurs. Much hotter, a lot more plants, therefore a lot more oxygen. That's why the dinosaurs are big, is because there's more oxygen to breathe. I mean, it's just like kind of, this is just so ABC, and you just say, how can people look at these ABC facts and pervert them into, we didn't do nothing. We just burned a lot of carbon. How could that change anything? Well, because it reverses this 100 millions of year process that caused the Earth to cool into what it is now. It's cold by comparison to what it was 300 million years ago. A lot colder. And that change was caused because trees die badly. Okay, they're not biodegradable. Not very. They don't get back into the environment. So they just take stuff out of the environment and bury it. And we unburied it. And we released all these corpses, these demons.
Converted into coal or oil.
Yeah, I get
And
the
some
idea.
of that fuel was converted into hot steam.
Yeah, but the hot steam, they say, it was converted into hot steam. No, it was converted into black smoke full of carbon. Okay, we put it back up there, and at the rate the biosphere can deal with it, I mean, it's up there for 1,000 years or whatever. It's up there for quite a long time at the slow rate that the current biosphere can consume it. So we're definitely pumping it up there a lot faster than the current existing biosphere can rebury it. And obviously we're killing all of the grave diggers. The rainforests and all the places that are digging the grave for the carbon. We're destroying all of those sinking mechanisms. And so we're just making it worse, because now all the stuff that ends up dying, it doesn't get buried anymore. All the poo.
Or something that turns a turbine or runs a motor. And we get orderly mechanical energy out of that.
Except for the disorderly carbon we shoved back into the atmosphere. There we go.
Regarding the
There's a little bit of an honest picture. Okay, that's more like it. Thank you.
conversion of thermal energy into mechanical energy, and then mechanical energy back into thermal. More of that in the next film.
Alright, so anyway, not that I want to be preachy on subjects, but I mean, it just, some of these arguments are just so, you're just saying, what these people just are, hopelessly devoted to bullshit. And so, well, it's like the Trumpies, right? I mean, the man is a deplorable, despicable pile of shit. And he's their hero. And you're just saying, how does somebody make a hero out of that asshole? I mean, this guy who earned nothing, has failed at everything, is dumb as a fucking, you could just, he's dumb as some the average 13-year-old, I'm sure, could pass more tests than Donald Trump can. And it's just amazing, the devotion. Why? Because, they want to fly the Confederate flag again, It's just pathetic. So anyway, yeah, so this is all so fucking hopeless. Human beings are just despicably stupid. So anyway, yeah, that's all. So anyway, sorry about the sink. It just seemed like it's broken. So I don't know what broke it this time, but shit happens, as they say. I probably should have just done this, right? Should turn the camera off and then turn the camera on. Yeah, see, that's all better. Yeah. So anyway, should have done that. Yeah, it really wasn't much work, was it? No, it wasn't. Okay, so my bad. So, till the next time, I guess we'll do the little thing with the help. This has been a DraftScience video presentation. Just talking to the window, talking to the carbon dioxide, because it's pretty much the smartest thing on this planet. Because it's not dumb. See, the whole trick is, to be smart is not to be dumb. Alright, it's all about not making messes and not making mistakes. It's not a, it's just, it's that simple. Playing this game is just, it's like painting or drawing, or don't make errors, don't make mistakes, and then everything will be okay. So as long as you're not doing something wrong, you'll end up doing something right. And it's the same thing with thinking. As long as you don't get some stupid, dumbass notions in your head, then you'll have right notions in your head. It's that simple. If you don't have the wrong answer, you'll end up at the right answer. It's like magic. But you can't even figure that out. Shit. Alright, so till the next time and such.